Hi, let's review about the polar rectangles. The reason this is called a rectangle is about this part r and theta, where r and theta is varying freely from a to b and alpha to beta and not depending on each other. So whenever two variable varies like that, if you look at the r theta plane, not xy plane, r theta plane, then it looks like rectangles. But how it translates to xy plane, it's like this, where these two lines, rays coming out from the origin, is where the theta and theta values are fixed. Alpha here and beta there. In between is going to be some value alpha and theta between alpha and beta. This circular sector part here is where radius r is fixed, and this part is where this rb is fixed. So in between here correspond to this region right there. So that's the polar rectangles. So we're using these polar rectangles, we want to enter the Riemann sum, which is the part of the definition of a double integral. So here is the tiny piece from that division of the polar rectangles. So r, the radius, is divided into n pieces, and theta is divided into m pieces, not necessarily the same. Let me show you the other part. So this, if you see these circular arc going around like this, that's with different values of r. So that corresponds to division of r value. And you see these rays coming out, that's the different angles coming out, that's the division of this theta value. So if you divide these thetas and r's into n and m, irregular partitions, then it's going to create these little tiny pieces. Once you have these tiny pieces, that if you look at the kth interval along this r part, the radius, and the jth interval of the theta part, you have this set. The part of the Riemann sum requires a choice of this point in that region, called kjth region, for example. Then this is a free choice, right? So we can choose any points in there and consider the sum. That is the difficulty, and at the same time is the most powerful part of the definition of the Riemann sum toward to the double integral. So here I'm showing all together that the Riemann sum is that this delta akj is the area of this one, also sketched it here. And this is the function value for that point we chose inside of that kjth region piece or cell. Then you plug it into the function fx. So we're going to erect a tiny building, tall building relative to the size of the base here. And that's going to be the height, could be negative number, and multiply by the area of the base. So that if you sum all up, and that's going to approach this double integral, if that double integral exists. However you do this, however you chop it up and what point you choose, is going to go to the same number that is denoted by this double integral symbol. So here's that tiny piece area. See, the only deal here is that doing this computing area of the circular sector, tiny sector here, doing this carefully is the main deal about this this part here. So this is going to be the analysis of that tiny sector, which is sketched here. So let me zoom in a little bit like this. So that's that piece, the kjth piece. So this is a kth interval along the r, and that's the theta j minus 1 and theta j part. So we're going to carefully calculate this area. So we look at this circular sector, the big piece here, that's the origin, 0, 0. So we use the formula half times the radius squared times the theta in radian. We're going to use that formula. And then we're going to subtract off this smaller piece of circular sector, which has radius r sub k minus 1. Then we're going to left with this part, and that's going to be the area. So let me show you the formula part. Alright, I think I fit in a little bit. So that's denoted by this delta akj, and that's the formula I was talking about. Half times r squared times the angle here. Notice that for both cases the angle is the same, the radius is changing. So we have this theta k and theta k. and this is the area of a smaller circular sector, half times RK minus 1 squared. So if you subtract off, that will be the area right there. Okay, so here's a little thing I'm doing that book actually calculates this in an exact way, but this is also, the following is also a neat idea, and then we might be using for later on for more general cases. So let's look at it more in a theoretical way. So here it is, that if you factor out the theta k and theta k, and 1/2 and 1/2, what you're left with is RK squared and RK minus 1 squared. So that's written here, RK minus 1 and RK minus 1 squared. But I had this RK minus and RK minus 1 down there, and if you look at this part, that looks like the mean value theorem. Function involved in this mean value theorem here is x squared function. X squared function. For that x squared, we have two different input here. That is, this two different input is a subtraction. The difference is written there. This is exactly the setup of a mean value theorem. So mean value theorem says this value is going to equal to the sum value of a derivative, exactly equal to the sum value of a derivative. So this derivative of x squared is 2 times x. So some value in between RK and RK minus 1 will get this value, RK tilde. If you do this exact calculation, of course, then it turns out, because it factors nicely, and there's an exact way of doing that. But looking at this theoretical way is also important whenever that type of thing is not possible, exact calculation is not possible. This will be a powerful thing. So I shifted it a bit. So this part simplifies to this common factor half times the theta k times this one. Let me slide a little bit slowly here. This is exactly delta k there, delta rk. So if we want just the numerator part, you will multiply delta rk to this mean value result right there. So I forgot to do that. So here's rk and theta k multiplied, and there is this 2 times rk tilde, and 2 cancels, so you have rk tilde. All right. Book has this result as a rk plus a rk minus 1. In that case, you have to deal with a little bit of error in there because it's not exactly just r or anything. But if you treat it this way, the error is completely handled nicely, so you don't have to worry about anything. So again, rk tilde is some intermediate value in between rk and rk minus 1. So let me show you this Riemann sum again, and then help you to remember what is that we're trying to do here. Is that this double integral in terms of x and y has this weird region D. It's inconvenient to do this iterated integral. So we're about to write this x and y in terms of other variables. So maybe for the region for that new variable has a prettier region so that we can do the iterated integral nicely. So we're about to change this x and y and ak. Since we're trying this polar region, the coordinate system, this has obvious choice. X is going to be that r cosine theta and r sine theta. But if you look at this formulation here, then it requires everything written in terms of the star notation times the pieces, the area of the tiny pieces. That's our goal. If we try to change everything here into a new variable, it should be in this form. Everything in this star notation and times the area of the tiny piece. So what we need to do is that we're going to write everything here in terms of r star and theta star, right? If you choose those points and somewhere, let's say this is kjth piece there, region, then we have that point, and we have x coordinate, y coordinate there, but it has r value and theta value. So that will have rkj, and that will have theta kj. So that'll appear here somewhere there. And then this, because we're doing this rectangularly, this must be delta r and times the delta theta. So that's how it should change. From that we can easily pass to double integral. Again, the great thing about this freedom we have for these the star part is going to come into play. Really important part, and the whole reason I'm actually doing this in detail is to see this power and the mean value theorem. Sorry about this part, and I plan to just ignore it, and it's still there, but it's actually not bad idea to show this one here. So this is the Riemann sum before, and we have this r cosine theta in there. Okay, this is going to be the shape of the Riemann sum in terms of r and theta, with this rectangular r theta region. But main part is this one. Remember what this rk tilde was. Rk tilde is still there. What this one was, let me show you a little bit, is this mean value theorem. So this is not a free choice. There is this partition along this r value, or the radius, and then this rk tilde is determined. Alright? But Riemann sum has this freedom of choosing this rk star and theta kj star. So why don't we write this rkj star, the choice of that free thing, to be this particular choice, rk tilde, which the mean value theorem requires. So we have this rkj star completely fixed, rk tilde. It can be anything. That's the part of the definition of the double integral and the power of the definition of the double integral. So we have that, and it turns out there doesn't have to be any condition on theta kj star for this thing to work. So we have choice for rkj star fixed like this, special value, and theta kj star is free. You can choose anything. So here it is. The Riemann sum, the original Riemann sum, is rewritten with a different information. That x and y, right, xkj star and ykj star, that should be written in terms of r cosine theta and r sine theta. And we have to give a choice of what rkj star is. Rkj star, we chose that to be rk tilde. So here we choose rk, some free choices there, and that delta akj is exactly equal to this, not approximately. That's the whole point of this careful analysis I'm doing here. The delta akj, using the power of the mean value theorem, became exactly equal to rk tilde times these two delta value. I'm missing delta here, I apologize. Delta is supposed to be there, delta theta k. But we chose the rkj star to be this rk tilde, so that becomes rk tilde and rk tilde, or we should replace that rk tilde into rkj star, right? So that's actually written down there. So that rkj star had made a choice, and theta jk star could be a midpoint in between the theta j minus 1 and theta j. So we have made a choices. The point is that now we were able to rewrite the Riemann sum completely in terms of all the k stars here, and this one even is a star, and then rest of the part here is the rectangular length, length along this r axis and along the theta axis. So this is in the correct Riemann sum formula. All right. What is slightly better than what's in the book is that there's no approximate choices you have to handle here. There's no approximately equal anything. This is the Riemann sum, and it is supposed to approach. It's not approximation. It is supposed to approach this number. But if you have a little bit of a different value than stars, like rj and r plus rj minus 1 divided by 2, that's something like that, it's not perfectly in this Riemann sum form, and that was the gap. But a little bit have to fill in. But if you used correctly about the Riemann sum and this mean value theorem, then we can pull out this perfect one like this, and we have also the result that is supposed to approach this double integral. So every star changes to just a plane variable, every theta star changes a plane variable, and that is the same star go there, and this dA it's supposed to be that AKJ or BKJ, because it's a different plane, R theta plane. All right. The fancy name for that R is called Jacobian. That measures the proportion of one piece and another piece when we look at this substitution of variables. So let me zoom in here and then summarize what we have accomplished here using the mean value theorem and the power of the definition of the Riemann sum and the double integral. We were able to rewrite that integral into the following form, that x and y is replaced by the substitution, and there is this stretch factor called Jacobian, and how the pieces of the area is proportionally changing, so that factor. And the whole reason we are doing this is that with this change of variable, the region of the double integral became this rectangular region of dummy variable. All of a sudden you can switch to an Rn theta is just a variable, and this region they are changing is rectangular and totally free from each other. So iterated integral, it's very nice. Right, let's take a look at example. This is double integral of this quadratic polynomial over the region R, and region R look like this. The inside part here, inside boundary, is given by the circle equation x squared plus y squared equals 1. The outside one is given by x squared plus y squared equals 4. So that's radius 2. And it says in the upper half plane and bounded by these two circles and something like that. So that's the region. The key thing is to recognize this one as a polar rectangles. If I'm cutting this region in here, it's kind of similar to the one that we sketched here, but hope you be able to realize at any point in here on this boundary that theta is R value is always varying freely from 1 to 2, 1 to 2, anything like that. So given theta, R varies freely always from 1 to 2, not depending on the choice of theta. Anyone here is 1 to 2. Any value here is always varying 1 to 2. So R is varying from 1 to 2 freely. Okay? And given theta value. And theta can be anywhere here from 0 to pi, and 0 here, this is where theta 0 is. This is where pi over 2, and this is pi. So theta appears anywhere from 0 to pi. So hope you'll be able to realize that there's no dependence between R and theta, therefore it should be called polar rectangular region. So let me show you how the rest of the part goes. It's fairly easy if you kept up nicely with this integral part and calculating integral part. Just mainly it's going to be about the beginning of part that I'm explaining. So the whole thing about is this xy double integral being switched to r theta double integral. All right. So because these are rectangular polar region, the double integral will be 1 to 2 and 0 to pi. Now it's all about r and theta. And that's because we wrote theta inside the d theta dr, and you know by Fubini's theorem, it doesn't matter how you do it, to make sure this order has to be consistent with this order there. That's all you have to be careful about. Now this x and y is replaced by r cosine theta, that's x, and r sine theta, that's y part. So that whole thing. And the Jacobian factor is r, so r should go there. R is not constant, don't get that part wrong. It's varying 1 to 2 at each point here and there. The way the factors, how much is stretched is different. So you have to keep that R as a variable. And in the test, actually, I see that a lot, and for some reason R showed up here as a constant for many student solutions. So be careful in that part. So from here, it's simple calculation, but I wanted to point it out. When you do this exercise together like this, always the advantage is, since it's a video, you can pause it and do this calculation yourself. And this is how you're actually not falling asleep and do something yourself along the way. You can always pause the video and then do something yourself always. Alright, so let's say we got to this part. The reason I'm explaining here is that this is the rectangular region integral, iterated integral, and r and theta is nicely separated. Remember, there was a formula that if it is multiplicative, nicely separated like this, and if the iterated integral is over rectangular region, not the general region, so that these limits depend on each other. If it is like this, you can just pass each other, and we have one, sorry, this is supposed to be 2, I copied it wrong, and r squared and 0 to pi, and this one pass each other nicely like that. So you can easily write this double integral in terms of one variable integral like that. This is a second example, and also a double integral problem, but it's slightly different. This is the volume of the solid is not formulated as a double integral problem, but when we look at this bounding surfaces and figure out what the domain D is over which we're going to take the double integral. So that's the first thing we have to do. We have choices. Usually we look at xy plane, yz plane, and zx plane, and think about which one is the best one to do. So first I chose xy plane, not particular region, but by looking at the z equals 0 and z equals 1 minus x squared minus y squared. Didn't have much choice. It seems like z equals 0 is suggesting that we should look at xy plane. So here's xy plane there. And these surfaces doesn't give you much information about what we're looking at xy plane immediately. So let's look at it one at a time. Z equals 0 is going to be this entire plane, xy plane we're looking at it here. And z equals 1 minus x squared minus y squared is quadric surface, and the usual thing we do is let's see how this surface intersects this xy plane. So we wrote this z equals 1 minus xy squared, x squared minus y squared here, and set z equals 0. That's where this plane is. So if you set z equals 0, that's z equals 0. So if you rewrite that equation, then we get this unit circle. Okay? So the unit circle is sketched here. So this is how the surface intersects. And if you look up the tables of quadric surfaces, this is the actually elliptic paraboloid. Alright? But it's kind of upside down shape. But anyway, this is where the z equals 0 level, right? Inside is either positive, z equal positive, or negative. So we usually sample that point, something that's available, like 0, 0 here. So if you go back to this formula, plug in x equals 0 and y equals 0 there, then we have this value positive. So at that point right there, z value above there is a positive value. And this is where z equals 0, by continuity or using intermediate value theorem and things like that, you can assume that everywhere here inside is going to be positive. The z value is going to be positive in here. So that seems like already a good thing that they talked about z equals 0, so this entire plane, it serves as one boundary of this solid, and we're looking at this cut made out by this elliptic paraboloid, and we looked at each point inside here, that z value is positive. So it seems like starting from right here, z value, you go up there and being positive and come back down. So clearly we see that over this circle something is bounding above everywhere. And z is a function form, z equals something. So at each point here there's unique z value assigned up there. So that's probably it. Or whatever the shape up there, although it's simple knowing that it is elliptic paraboloid, this information is enough to set up the double integral. So here's the setup. That D, we're going to call that disk region. The inside the circle is going to be this D, and we recognize this region, circular region, as a rectangular region, polar rectangles. is that the r starts from 0, so I'll pinch down to 1 point right there. But that we recognize this as a rectangular region because this one exactly corresponds to that. There's little thing about this is 0 point right there, 0, 0, and all this is 0 to 2 pi when r equals 0, it's going to collapse down to 0 point at the 1 point down there. But that happens for just a one-dimensional domain, so called 0 to 2 pi, where r equals 0. Whenever r is not equal to 0, then there is no collapse. The some circle here with the positive radius, and it will nicely correspond to some one-to-one correspondence with the values here and r and theta. But if there are some points like this collapse to 1 point here, and the dimension of such points is just one-dimensional, and then we're doing this two-dimensional calculation for the double integral, and that's okay. The part is similar to the earlier example, so I rather want you to pause the video and try yourself and compare your answer with what I have in here. Alright, I hope you did it yourself, and make sure the only thing I'd like to say is that x and y is replaced by this typical polar coordinates, and there's this Jacobian factor. Again, it is the proportion of how this area is stretched and stretched out when we change the variable from rectangular coordinates to polar coordinates. And as you can see, the integral is a lot more pleasant than the other case, which is doing this rectangular coordinates over this d. Then it's going to involve square root of 1 minus x squared, something like that. Okay, next example is, I can make up this name. It's a general polar region. It's not polar rectangles. It's a general polar region. We will encounter two situations, and you can even make it more complicated. The standard situation is that given theta, r varies depending on theta. Compare this one with given y, x varies depending on y. Or given x, y varies depending on x. Think about those kind of situations, the general region in xy plane, something like that. But it is happening for polar region, polar coordinates. Given r, theta is varying depending on r values. Okay, so let's look at some examples. So here's the picture that given theta, alpha to the beta, so and alpha and beta is here, given theta, we're going to look at r value, how r is varying. So this is, I wrote here the r line is quite messed up right now, but it's r line, so r is varying. Here theta is fixed. This is the line where theta is fixed and r is varying. So if you look at this part, that's kind of smallest r value that is available in that theta value fixed. You start from there and changes all the r value, keeping this theta value the same, and that seems like the last value there. So r is changing, the arrow indicates that r is changing. So this is the example where theta is fixed and r is changing. Although it looked like a circle part, but we're assuming this is not necessarily a circle. So this n value right there is depending on your theta. If your theta is different, then this n value of the r value right there is going to be different, not always a or b, and like that. It's changing as theta changes. If you look at this upper envelope, it's quite clear. I exaggerated a lot so that you can see for different theta value and the limit, the r from here to there, the length is changing. It's not fixed, always a circle or anything. So that kind of thing. We've seen that for x and y. It's just happening for the different coordinate system. In sketching, when you sketch the visualize, you have to be a little bit more careful with the polar coordinates. So let me show you how the other one, when r is fixed and the theta is varying. So I think it's showing here. Let me make it a bit bigger. Okay, Okay, this seems like big enough. So this time, what is fixed here is r is fixed. So for example, if you look at this line, is r is fixed, and all the points in here, the r value is the same. Suppose 0, 0 is over here, and this is really the circle. Therefore, where r value is fixed. And what is changing here, therefore, is a theta value. Okay? Theta is changing going from here to there. And as I exaggerate it like this, the theta value, if the theta value is all fixed for the beginning part, then it's supposed to be straight line. That's where all the theta values are the same. So if it is wiggly like this, it's clear that theta value there, the angle from the origin, and theta value there, the angle from the origin, is different from for each of these different r value would start from. So this the theta value that we're starting here is different from that one and so on. So they're depending on choice of r. This is where r is something, and that's where r is something else. But along the line, r is fixed along this arc. So the beginning theta value depends on your choice of r. The terminal theta value here depends on choice of r. So we have a function of this r and r as a function of theta. So you can imagine this situation like this. But our textbook does. I don't think it has a problem like this, but they have the other case. But since we're thinking about dependency, I'd like to throw in, and this is definitely possible to think about, and it is not difficult to actually solve some problem about this type of situation. So let me show the typical one again. So I guess we're going to look at this example more than the other one. Alright, we are starting this general polar region with some slightly harder example. We're hitting this volume of solid right away. So we're computing the volume of the solid that lies under this elliptic paraboloid and above xy plane and inside this x squared plus y squared equals 2x. There's no z in it, so you can assume it's some sort of cylinder. Okay? So you might pause the video and try yourself a little bit, at least to understand the situation before you see the next part. That's always best way to learn mathematics. Okay, if you look at the problem, and we have elliptic paraboloid. Here's the problem again, elliptic paraboloid and xy plane and this thing. So by looking at this one, I immediately, okay, this is what we're going to sketch first, because that's going to give us the region D. So let's sketch that. So let me show you a little bit. So here's x squared plus y squared equals 2x. So it's not a circle or anything, but you can see from x squared and 2x you can complete the square. So here is how we complete the square. X minus 1 squared plus y squared. First you collect x squared minus 2x, and by adding 1 both sides, and you can complete it like this. Okay, so that's the circle with the center 1, 0, with radius square root of 1, which is 1. So if you sketch it, it looks like this. So this is not a circle really. Inside this thing means is a cylinder inside the cylinder. So whatever we figured out is hovering above here, that would be the cover over this region D. And let's look at the other part here again. Here it says above xy plane, this is xy plane, and this is elliptic paraboloid, it's lying above there, and this is the cylinder. And from this equation you can see they're all positive, so it's definitely hovering over in here. If not, and you have to figure out where the z equals 0, and it might cut out things like this, then figure out which one is lying above and which one's below. It's not that complicated, but it's something that you have to think about always. Again, z equals x squared plus y squared. Think about how this one intersects xy plane, especially how this one intersects inside this cylinder. If you set this one equal to 0, only spot that this one becomes 0 is 0 comma 0 is here. Other than that, every inside value here, the z will be positive. We are in this section of the polar region, so that's what are we going to do. But if this one was just a random problem thrown at you, and if you're especially doing this in the test and you have choices, and you can still do iterated integral along x or along y and something like that. But let's try the polar general polar region thing and see if that's nice or not. Well, obviously this is maybe not that obviously, that maybe it is the polar rectangles or not, but one way to figure out is that you turn this Cartesian equation, which is the boundary of this region D, change that Cartesian equation in the polar equation, and from there you can see if r is depending on theta or not. So r and y, x and y here, is replaced by typical polar coordinate conversion, and you don't multiply r or anything. That's only for integral Jacobian factor, and 2x is being like that. So this left hand side is simply r squared, because cosine squared plus sine squared becomes 1, and right hand side is just copied it here, and we're about to cancel r. Whenever we multiplicatively cancel this, then we have to be careful that r being a 0. So I wrote down r can be 0, that's satisfied. Otherwise we can factor that r, and we have this r equals 2 sine 2 times cosine theta. Okay, but as theta varies freely from whatever to whatever, and this r is going to be 0, so this case is included here, so I'm just writing it like this. Okay, let's see what this really means. I copy this circle again, and then I wrote down the polar version of the polar equation of this boundary, r equals 2 cosine theta. Because r is written like this, it clearly says that r is depending on the theta. So I guess the given theta value, like this, an arbitrary one chosen in here and in between, somewhere in between here, so it cuts 2 points. Given theta value, think about how the other variable is changing, which is r. So r is changing from here to there to cover all these points inside this circle. So definitely there is r equals 0 and ending up at some value here. And what is this value? And that's a boundary point. Therefore, it follows this relation, r equals 2 cosine theta. So given theta, r starts from 0, and then that 2 times cosine theta, and that's the length of this one. So while we verified it here, this is not a polar rectangle. The way r varies is not fixed, it's changing, right? So given theta value, it's obviously changing. So we got that part, and how r is changing from there to that. Next thing we have to figure out is how this theta is changing. Clearly, theta can be this type of 45 degree from this picture, or it can be 0, or it can be over here, something like that. But it's not clear what's really happening. What is the angle we should, how much we should push it up here. So for that, I approach it in the following way. So let me show you here, and that's what I wrote down, is how is this theta varying? What is this alpha and beta? This is not polar rectangles, but if we start from the theta, then it must have this absolute constant. Right, before we actually look at that problem that we have, let me just use examples. It's a different example just to clarify the meaning of theta varying from alpha to beta. So this is again the situation where theta is given and r is varying from 0 to some theta value, which is not necessarily equal. R varies from 0 to this value, and it's not constant, it's depending on theta. That's what I'm trying to say. So it seems like when theta equals 0, r is going to vary from here to there, and then that's that. It seems like that's the end of it. So if you put this theta value here, there's this r value varying from here to there. But if you put the theta value over there, doesn't seem like any r is assigned. So let me use this Paint to show you clearly. Paint software. So okay, this is what I mean by this, and then here, and that seems like a theta value. We still have some R value assigned right here, but if you choose this theta value right there, then there's no R value assigned. It's kind of ended it. So here is these kind of last theta value you want to consider along that turn, and then the other one, of course, is the last theta value you want to consider. Okay? So in that regard, intuitively, that, okay, let me just consider this one, which is pi over 2, then is there R value assigned? It seems like it's there, 0, right? But nothing else. It's kind of weird. But if you look at this direction here, there's absolutely nothing above it, and here it's a 0. So, and it's still very confusing. But if it is like 89 degree like that, and you can see probably cuts through a little bit over here because of this tangency. Whenever you tilt it a little bit, there will be some cutting point. All this thought, right? But let's look at it more carefully. So I guess it's about showing, okay, if you put this pi over 2, you can see from the picture it's probably the only point, only in a section with a circle, or only R value assigned there is a 0. So we're going to verify that by looking at this equation, and this is what I mean by it. So okay, when is this R equals 0? Because all the boundary is governed by R equals 2 times cosine theta, therefore it should be this one. And if you solve this equation, it says theta equals negative pi over 2 and pi over 2. So before you reach that negative pi over 2, pi over 2, that was the one that we were looking at, and it's going to be always have some R equals positive number, not 0. The only angle that reaches pi over with R equals 0 is pi over 2. So it'll always intersect a little bit tiny if that wasn't quite clear from that picture I drawn there. So I guess it says that we have to take this negative pi over to the pi over 2. In between that, at pi over 2 is kind of unclear, but in between that pi over 2, negative pi over 2, we always have this value R equals 0 and something else, because only time that R becomes completely 0, the other one being collapsed to 0, is these two angles. So although it's not the typical cut that you clearly see, but it is one of the cases that we have to consider as the general region that where R is depending on theta. So that's why the integral is set up like this. So given, let me show that again. Given theta value, R varies from 0 to 2 cosine theta, right? So, and here's again, from 0 to 2 cosine theta. Given theta value, R varies from here to there. And there is this Jacobian factor. So it's not showing completely. Let me move it over here. So that's the formulation. So solving this one is, this whole thing is going to be just R squared inside, and out there R cubed, because cosine squared plus sine squared. So here's R cubed, and since we're doing this one for R first, so that's 1/4 and R to the 4th, and evaluated these 2 points. And that brings us down to this one variable integral. Alright?